There we go. Yep. See ya. All right. So you guys know kinetic energy, average speed of molecules. What else is there? Effusion, which is like diffusion kind of. And then the fourth thing would be when the ideal gas law, PV/nRT, doesn't work. Okay, so those four things. So it's the last 2 pages of your notes there. I think it's page 7, page 8 maybe. Is that what it is? 7, 8. There's no math involved in this. It might look like there is, but there's no math involved. Okay, just so you know. Hopefully these guys online can see this. So here's kinetic energy first. Energy of motion. Kinetic energy is energy of motion. So you could answer this without looking at anything on here. How do you make molecules of a gas move faster? Heat them up. As simple as that. If you've taken physics, kinetic energy is 1/2 mv squared. You know what m is? Mass. You know what v is? Velocity. They put this on the little formula sheet on the AP test, and it confuses people. For some reason, with molecules, the mass of the molecule does not affect kinetic energy. So all you need to know for this is this. If you increase temperature, increase kinetic energy. Molecules move faster, they have more kinetic energy. That's all you got to know. So if I say, who has more kinetic energy, H2 or O2? You don't know. Okay, what if I say this one's at 100 degrees Kelvin, this one's at 200 Kelvin? Now you know it's oxygen. You don't have to know anything mathematical about it. Higher temperature, more kinetic energy. Higher temperature, more kinetic energy. That's pretty simple, usually. All right, there's that. Average speed of a gas molecule. U. U is average speed. U is average speed. That's weird. There's a little formula. You don't really need to know this formula, but we used to have to do math with this. Now there's no math involved, but the formula is U is speed. Average speed of a gas molecule. I don't even know the formula, to tell you the truth. 3RT over MM. Is 3 ever going to change? That's a constant. R is a constant. It's not the same constant you're used to, though. It's actually 8,310. Don't worry about that. So temperature can change. What do you think MM is? Molar mass. Okay. They usually will say, when they ask you questions, they'll say, what is the root, mean, square, speed? That just means speed. When you say, what is the root, mean, square, speed? They call it the root, mean, square, speed because it is the square root of it. They always put that on there. It just means the average speed of a gas molecule. Okay, average speed of a gas molecule. So what's one thing that affects the speed of a gas molecule? Temperature. And as temperature gets bigger, temperature goes up, speed increases. That's U. We'll just put speed. Speed goes up. Molecules move faster. What's the other thing that affects the speed? The molar mass. Fat molecules move slower. Okay. Big molecules slow. So increase the molar mass of a molecule, decrease speed. Sure, we did talk about that in here, didn't we? So kinetic energy is only affected by... No, kinetic energy is only affected by temperature. Speed is affected by temperature and size. Okay, that's a little bit weird. We could kind of get into that more, but that's all you have to know. Kinetic energy, only temperature. Speed's affected by both of these. Now here's the deal with speed. It's called the root mean square speed. It's the average speed. So if there's a gas molecule right here flying across the room, what happens when it hits this wall right here? What happens with speed? Down to about what for just a split second? Down to about 0. Comes back over here, runs into another molecule. Its speed hits 0 for a second, speeds back up. So it's always the average speed. There's always some molecules going really slow for just a split amount of time, some going really fast. So you can't just say, hey, oxygen's traveling 450 miles per hour at 10 degrees. Some molecules are moving faster. So it's an average of all the molecules, okay? We'll come back to that in just a minute. Those are fairly easy things, I think. You have to remember that kinetic energy is only temperature, though. You ever heard of diffusion? Third period did not know what diffusion means. Like if I light a match over here, who's going to smell it first? Me. I'm closest to it, right? Eventually, will Bryce probably smell it eventually across the room? Eventually, more than likely, right? But it's going to take a while. Those molecules will diffuse. They'll go from an area of high concentration to an area of low concentration. Now, if you come back in an hour, do you smell it still? More than likely not, because those molecules continue to spread out to where you might not run into them anymore and smell them anymore. That's diffusion. Okay. Effusion, which is really weird to me, is the flow of gas particles through tiny pores or pinholes. The best I can think of in this is like balloons. Do you guys know balloons are a little bit porous? There are small pores in balloons. Now the gas doesn't go flying out of there very fast, but what happens to the size of a balloon over days? It shrinks down. It's because the gas is getting through the pores. Okay, the gas is getting through the pores of there. So what do you think affects how fast the gas goes through those pores? If you just had to take a guess of how fast that gas moves through the pores. So the size of the pores would matter, but let's just say it's the same size pores. So molar mass matters. How do you think that affects it? Well, in other words, let's do this. So if we say, if you increase the molar mass, you have a bigger molecule, what do you suppose that does to the rate of effusion, how fast the gas makes it out of the balloon? So it makes, we'll say, slower effusion. What's the other thing that you think makes a gas escape faster or slower? Temperature. So if we increase temperature, now the molecules are moving faster. They have more motion. They have a better chance of making it through one of those openings. So increased temperature increases the speed of fusion. That's my horrible handwriting. So if I go to this, let's say, okay. So there's a gas. There's tiny little openings. Okay, small gas, big gas. What's happening to the small gas particles? They're making it through the openings a lot more often, right? They have more motion, a better chance of making it through there. How could we make it so these? How could we make it so those effused at the same time, same rate? So I could increase the speed of these. Nothing to do with pressure. Nothing to do with pressure, but I can increase the speed of these by increasing the temperature, or make that one colder, slow it down. So effusion, molar mass, and temperature affects it. Molar mass, temperature. Going through this fairly quickly, but I don't think it's a whole lot of stuff to know. Good there? So kinetic energy is only affected by temperature. Average speed of a molecule is temperature and molar mass. Effusion is temperature and molar mass. All right. Go to next page, where it says distribution of molecular speeds. Distribution of molecular speeds. All right. This tends to be on AP tests, this little graph. This little graph like this. And it is, I don't know if I can increase this size. I can't. So this is speed. Showing speed down here. Average speed of a gas molecule. So if we had say this is a sample of oxygen at 25 degrees Celsius. This is number of molecules. So the area under the curve is the relative number of molecules. So where's faster speed, where's slower speed at? More to the right is faster speed, more to the left is slower speed. The size of the hump doesn't mean anything other than that's the number of molecules underneath there. So notice at any given time, some molecules are traveling approximately 0. Why? They run into something, right? So they slow down. Some molecules are traveling really fast. The average is somewhere out in here. The average would be probably the highest part of the curve. Most molecules are traveling that speed. Make sense? So most molecules are traveling there. So what if I had a gas at a higher temperature? Higher temperature. And I asked you to draw the curve on there showing a gas at a higher temperature. It'd be further to the right, but not as high. Like, it would not be this. Why would it not be that? That's the same height, but would you still have molecules traveling zero at some point in time even though the gas is hot? You would still have molecules traveling zero even though the gas is hot. So you still would have to start your graph here. It'd be the same relative number of molecules underneath the curve. Just now the average speed is out that direction a little bit further. Okay. The AP test tends to put this on multiple choice. You know what they do? What do most people choose? Here's one of the choices they give. People are like, oh, it's got to be the faster one. It's the higher graph. Okay. I think there's one of these on here. Yeah, so here's a cold gas. It's the highest one, but it's the coldest because your average speed would be back this direction. That makes some sense. What if I go back up here? What if this was carbon dioxide? This gas is carbon dioxide at like 25 degrees Celsius. And I want you to draw a graph of hydrogen at 25 degrees Celsius. So same temperature. Would they be the same speed? Why not? Hydrogen's smaller, so it means it's faster or slower? Faster. So the graph needs to be farther to the right. So again, it'd be some kind of curve out like that. Same area underneath the curve, same number of particles. Okay, but further to the right. If you look on this sheet, by the way, the average speed of an O2 molecule at 25 degrees Celsius, that on there, 482 meters per second. I have no idea how they measure that. Average speed of an H2 molecule at 25 degrees Celsius is 1920 meters per second. There's a big difference. Why is H2 so much faster than O2 at the same temperature? Way smaller. A lot faster. A lot faster. Like me. Awesome. That's probably not going to be. I don't think I want to. Because then it'll be the opposite way. All right, you good there? Last thing. Real gases. As opposed to fake gases. Now, so here's what this is. The ideal gas equation, PV equals nRT, is very, very accurate. Okay, so PV equals nRT. Like, you do real life stuff with it. Like when they make airbags. Airbag, you have a collision, two chemicals go into a container together, they produce a gas. Okay, they know I use 0.213 grams of this and 0.474 grams of this, and I get 1.375 liters of gas produced. Okay, if it's more than that, that airbag is going to be really hard. You're going to hit it and it's going to break your nose. Okay, they know they can plug into this and get a very, very accurate answer at fairly normal conditions. Around 1 atmosphere, anywhere from probably like negative 15 degrees Celsius to 100 degrees Celsius, even from like 1 atmosphere to like 4 atmospheres, it's pretty accurate. But then it starts not working at extreme levels. Does that make some sense? It doesn't become very accurate. Okay, like we'll do a lab Monday, and you can plug into this and get a really, really accurate answer in this room. Okay, it works out very well. Here's when it doesn't work. When the molecules of the gas get really close together, this is not very accurate. When the molecules get close together, it's not accurate. So what makes molecules of a gas get close together? High pressure, low temps. If you have either one of those or both of those going on at the same time, this becomes fairly inaccurate. So I think I have that on here somewhere. Yeah, right there. Make a little star, note that it. This does not work very well. When the pressure's high and the temperature's low, because the molecules. So remember we were saying that why does the size of molecules not matter for how much space a gas takes up? There's always space between them, right? There's always area around them. Well, when the molecules get close together, now there's not really very much space between them. They might actually be touching each other. So then this doesn't work. And there's two reasons for that. Okay, one of them is the particle size starts to matter when the molecules are close together. You know, like if I tried to shove you guys into a closet, bigger people, we couldn't fit as many big people in there as we could little people. Okay, the size of the particle starts to matter when they get close together. And the other thing is molecules have attractive forces, which you guys apparently don't know much about. Intermolecular forces, you might know a little bit about intermolecular forces. Okay, you guys like hydrogen bonding, London dispersion forces, you maybe don't know very much of that. But particles, when they get close together, they have attraction for each other. Some molecules like each other a lot more than others. So that affects the volume of a gas as well. So know that it doesn't work very well at high pressures, low temperatures. It gets off for quite a bit. Let me show you something. Here's how much it gets off. I don't know how they, well, I guess you can know how to measure this. But. So here is deviation. These guys won't be able to see anything online probably, but it's all right. Here's O2, okay, and it's telling you how much, what percentage the ideal gas law would be off. So like you plug into it, you plug into it and get an answer of like 20 liters, and you actually go do something with it and you still get 20 liters. That means it's not off at all. Does that make sense? You know, if you're getting the right answer when you actually do it in real life compared to what you got in the equation. Well, at 1 atmosphere, 50 degrees, 0 degrees, and negative 50, it's pretty accurate. At negative 50, you're off by negative 0.2%. So your answer you get in PV-nRT compared to real life is pretty close. Notice if you get to negative 50, really cold, and 100 atmospheres of pressure, you're off by 19.1%. Your answer you get from the equation compared to real life would be off by a lot. But I can't think of much you're going to do at 100 atmospheres of pressure on Earth or anywhere. Even 10 atmospheres of pressure would be crazy. And at 10 atmospheres, the most this is off is 2.1%. Now for CO2, it gets off a lot more. At 50 degrees and 10 atmospheres of pressure, it's off 4%. At 50 degrees and 40 atmospheres of pressure, it's off 17.9%. And that's mostly because CO2 molecules are big. They have fairly strong attractive forces. Okay, so it starts to get off, and it turns into a liquid at a point in time in there. So anyway, it's off a little bit in there. That's fast. Good with that? All right. Good to see you guys. Whoever's on here.